So now, without further delay, let's begin today's event, sponsored by ZestFinance and hosted by American Banker. It's my pleasure to introduce your moderator for today, and that is Michael Sisk. Mike, you have the floor.
Thanks very much, Greg, and I would like to welcome the audience. Once again, we are very grateful that you have chosen to share some of your busy day with us. We know that your time is valuable, and we will honor that today with what I'm confident will be an engaging 60 minutes or so of discussion. Once again, our topic today is identifying better borrowers, how machine learning can drive your growth. And my name is Mike Sisk. I am contributing editor at American Banker. I'll be your moderator today. I've been a New York-based journalist for about 20 years, and my articles have also appeared in Barron's, Crane's New York Business, Inc., Institutional Investor, Strategy and Business, and Worth. And I am very, very pleased to introduce our speaker today. Douglas Merrill is the founder and CEO of ZestFinance, a Los Angeles-based financial technology company that uses machine learning and data science to help lenders make more accurate credit decisions. As the former CIO and VP of engineering at Google, Douglas oversaw all aspects of internal engineering and technology and drove multiple strategic efforts, including Google's IPO auction in 2004. He also served as COO of New Music at EMI Group and as SVP of Infrastructure and HR Strategy at Charles Schwab. Previously, Douglas was an information scientist at the RAND Corporation. Douglas is an experienced speaker who has delivered keynotes and fireside chats at previous Money 2020 events and other high-profile industry conferences. He holds a PhD in cognitive science from Princeton University and is the author of Getting Organized in the Google Era, How to Get Stuff Out of Your Head, Find It When You Need It, and Get It Done Right. And yes, we are very, 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 very pleased to have Douglas with us today. And just before we kind of really get going here, I wanted to just reiterate one housekeeping item that Greg mentioned, and that is we do have time set aside at the end to take some questions. Usually we've got about 10 minutes or so. You don't have to wait till the end to put your question into the queue. You can do that throughout the hour as the question occurs to you, and we really encourage you to do that. And if for some reason we don't answer your question in the time we have today, sometimes we run out of time, sometimes it's just a question that's better answered one-on-one, we will definitely follow up. So please, your voice will be heard. Please ask away. We really do want to hear from you. Okay, so just a little quick primer on ZestFinance. The mission of ZestFinance is make fair and transparent credit available to everyone. The company was founded in 2009 by Douglas Merrill, and it's located in Los Angeles, as we mentioned before. It has more than 100 employees, primarily comprised of data scientists, engineers, and business analysts from top institutions. And it's a company that's been getting a lot of attention in news outlets such as the Wall Street Journal and The Economist. So definitely a company that is getting on the radar screen of quite a few places, and we are really happy to have Douglas here with us today. So let me go ahead and take us to this slide, this agenda slide, and I will officially turn things over to Douglas to kick things off. Douglas, you have the floor.
Hey, thanks very much. So this is Douglas Merrill. I'm the founder and CEO of ZestFinance. I'd like to apologize in advance for the fact that I have a cold. And so if my voice sounds like I'm channeling an 80s rock star, please forgive me, and I'll try to cough quietly. What I want to talk about today, hopefully we'll have some fun and cover some interesting ground. When I founded Zest nigh on 10 years ago, the question that everyone had was, why would machine learning have any impact on finance at all? Like, why would it even be relevant? And I would just try and answer the question, and I would get people, they would tilt their heads at me, squint their eyes, and say, well, that's a really dumb idea. So it turns out, 10 years on, that it works. And I'm going to go through some results about why it works. And I'm going to then kind of poke you all a little bit to say, if you're not on the path of machine learning in your lending business, I think your competitors probably are. And as a result, you probably should get on the bandwagon. If you're on the bandwagon already, great. Welcome to the fray, and we'll just have some fun chat today. But where I want to spend most of my time is a little bit. It's not sure if it's controversial or just surprising, but the math is not the hard part of machine learning. The hard part of machine learning is actually all the stuff around the math. The math is hard, and we'll talk about hard math, but there's a bunch of other stuff which has been fairly systematically ignored through the process. And if you get it wrong, you're going to have a really bad day with some regulators knocking on your door, with documents that you just don't want to see. So let's chat about that today. So first thing, let's talk about machine learning underwriting working. So a theme throughout this talk, is that the numbers are all from ZestFinance clients. I'm not trying to make a sales pitch here, so I'm not going to talk a lot about what we do or how that we're wonderful or whatever. But the data is not made up. Is what I want you to understand. It just turns out that simply sticking machine learning in front of your underwriting process, it just really works. It can save the smallest approval rate increase we've ever had was 8%. We regularly see more than that. Actually, normally we see 33% or more decline in losses, and that can end up being a really big number. It just works, and the beauty of the math and the better use of data is it allows financial institutions to broaden their reach by improving their approval rate while maintaining their current loss rate or even lowering it. And that's a pretty sweet thing to the business side for the technology and the risk organizations to offer. It works across geographies. It's not just a U.S. thing, and it's not just an outside the U.S. thing. You can sort of find good data points across at least these three geographies. One can imagine also adding South America and Africa, but we don't have business there. And it works across credit domains. Initially, once I first started convincing people that there was some hope for ML in finance, the answer I always got was, oh, okay, but only in subprime, or only in subprime installment, or and that just turns out, again, to not be entirely true. We see benefits across credit cards, autos, all kinds of different installment loans, specialty loans like power sports. Like we see the benefit of ML across a wide variety of credit domains. But it's not magic. ML helps your underwriting by doing some stuff. So let's talk about what it does. Specifically, it finds better borrowers. This slide is an image that I don't like at all. It shows the chimerical benefits of machine learning by arguing that the left-hand side of the image is a linear model, and because the linear model is linear, i.e. a line, it mischaracterizes some samples. So it marks some orange circles as if they should be blue, and some blue circles as if they should be orange. Those are marked with X's in the diagram. And the right-hand side is the nonlinear machine learning model, which, lo and behold, categorizes them all correctly. So it is true that linear models are linear, but you can approximate a curve by combining linear models, which is the reason that many of you have a decision tree on top of a whole bunch of linear models. That's what that does. So the linear versus nonlinear is actually not the interesting part of traditional machine learning, traditional underwriting versus machine learning-based underwriting. What's really interesting about machine learning is that you can use more data and you can use it more effectively, which protects you from the two horrible bugaboos of logistic regression, which is logistic regression just mathematically fails in the presence of missing data or erroneous data. And in large parts of the world, the modal applicant has either missing or erroneous data. In large portions of the United States and Europe, many borrowers, although maybe not the modal borrowers, have a large amount of missing or erroneous data. So the failure cases where machine learning is helping you, it's not the cases where every piece necessarily, or where every piece of data is perfect, because logistic regression works reasonably well in those cases. It's the cases where every piece of data isn't perfect or is partially missing. So just for fun, let's build a model. In this case, let's build a model to predict gender. Now, for everyone in the room who is in financial services, obviously you should not build an underwriting model that includes or predicts gender. There's that whole ECOA thing, and if you're not sure what that is, you probably should go meet a lawyer. So we're not really going to do this. We're going to use this as an example to describe some interesting characteristics of ML. So if I asked you to predict whether an arbitrary person was a man or a woman, the first thing you would say is height. Men are generally taller than women. That is generally true, but height is distributed with too many outliers. There are too many tall women and too many short men. To wit, a woman named Sandy Allen, who's the tallest American woman who's ever lived. She passed a few years ago. She was about 7 feet tall. And a man named Dylan Postal, who's still alive, who's about 4 feet tall. And Mr. Postal is a professional wrestler which I think is got to be the best story ever. But because of outliers like that, actually height doesn't give you a perfect model for gender. So you're like, okay, no problem. I'll add weight. So I have height plus weight in my model because men have higher testosterone levels. Testosterone tends to cause increased muscle mass. So for the same height, a man's likely to be heavier than a woman. Totally right. And after puberty, your model is now quite good. The problem is your model now thinks that all kids are women. About 50.8% of the population in America is women. With this error, you're going to be predicting about 68% of the population are women, and that's not correct. You say, okay, no problem. I'll add birth date, because now I have age. So now I can have height, weight, and age, and my model's really, really good now. Okay, cool. Not a complicated model, but isn't it interesting that if I had asked you 5 minutes ago if age had anything to do with predicting gender, you would all have said no. This is a really easy model. You could compute this model on a slide rule. But it is indicative of one of the powers of machine learning, which is machine learning can use different kinds of data and use them more effectively. So height and weight and birth date, or height and weight and age if you prefer, are all distributed differently. They don't look, none of them are normal, none of them are approximated by the right distribution. So a logistic regression is going to try and shove them all into normality and assume they're not related, which is false. You'll still get an answer because it's a simple model, but you'll get the wrong answer. Machine learning allows you to say, okay, I don't care about the fact that height and weight and age are not distributed normally and are related. So you can use the data you've already got far more effectively. And in fact, in one of our clients, we found that almost 2/3 of the credit lift, of the credit improvement in the first model, was caused not by new data, but rather by using the data they already had more effectively. So, for example, you could use the trend in bankruptcies versus actual bankruptcies. You could use call history logs for previous borrowers that kind of are similar to, on some characteristic, new applicants. You can use the data you already got more effectively. People often conflate machine learning with big data. And although they're related, they're not necessarily the same. And I'm going to come back to this later on in the implementation section where I point out that you don't have to solve your data problems to be able to start your ML journey. Practically, what an ML underwriting does is do a better job of sorting applicants, right? Machine learning is not magic. It does something. And what it does, ideally, is try and identify people who look like they're high credit quality but who actually aren't. And equally importantly, find people who look like they aren't credit quality who are. So the blue line here is was our client's current model in production, previous model in production, excuse me. The yellow line, forgive me, is the machine learning model. And what you see is that it's got a whole bunch of people, and the x-axis is deciles, where 1 is the worst credit and 10 is the highest credit, or 1 is the highest risk, if you prefer thinking that way, and 10 is the lowest risk. So generally good credit to the right, bad credit to the left. And what you see is that a bunch of borrowers were moved from the right-hand side. On the right-hand side, you see that the yellow line is below the blue line, which means there were lower defaults in those upper bins. But bins 1 and 2, the yellow line is higher than the blue line, because what the model did was grab people who are going to default who looked like 6s, 7s, and 8s and push them down to 1s or 2s. It's that rank ordering, which is the heavy lifting done by the machine learning, and that's what you should be paying attention to as you're beginning to implement machine learning on your premises. Is like what happens with those swaps. In fact, let's talk about swaps for a minute. This chart is a little bit complicated, and I apologize for that. It's a little bit of an eye chart. You read this chart from top to bottom. To set up the chart, on the left-hand side, so you see in the middle of the chart, you see 1 through 10. Those are the same deciles you saw in the previous chart, where 1 is high risk, and generally kind of not people you want into, and 10 are low risk, and who are generally people you want to get approved to. You can see the sort of the shading on the right-hand side shows that roughly from decile 7 to 10 are people are getting loans, and roughly from decile 6 to decile 1, people are not getting loans. And what you'd like to see is that the models sort of seem similar, or you can. You don't want to see your machine learning model taking people that were ones before. Your current model thinks people are terrible, and your machine learning model decides they're tens. Radical movements like that suggest a problem with the underpinnings of machine learning. Let me take a step back for 1 second and talk about that. Machine learning is discussed often as if it's magic, as if it solves the world's problems without even trying. But that's not really true. There are some give-backs in machine learning, some things that machine learning doesn't do well, and notably, machine learning models are spiky, which is to say that as you make subtle changes in credit applicants, all of a sudden the output could be hugely different. So you make a little tiny change in one input, and all of a sudden things change dramatically. And that's called a steep gradient. Many machine learning models have steep gradients as part of their power, but much like many of our greatest strengths are in fact our greatest weaknesses, it's the great weakness of machine learning as well. Things can make huge changes from small inputs. That's unstable and therefore should worry a risk officer. One of the things that we think you should pay attention to is which credit moves to where. So let's look at this diagram again. So that's its context. If you see in the top, you see a whole bunch of dots above the 6. Those are people. Logistic regression models tend to be pretty chunky. They tend to drop. They don't drop people evenly across the space of 1 to 10 unless you force them to. So you got a whole bunch of people in a 6. So those people are going to get denied. And then the orangish arrows show the model, machine learning model translation from the original 6 to the final score. So for example, you see an arrow that comes from the 6 and goes all the way to the 1 and gives a 1 dot. And what that tells you is that one of those applicants was found by the machine learning algorithm and said, no, this is not a 6, this is a terrible 1. You're still not giving a loan, but you're putting people in a different distribution. And similarly, a few people were found to go from 6 all the way to the right to 10. So that machine learning model said, hey, you don't think this person is great, we think they're great. But almost all, the vast majority of swaps went from 6 to 5, 6, or 7. That's great. You would like the changes to generally be marginal. And it just happens to be that enough people went from 6 into the 7s to increase the approval rate of these folks by about 15%, while keeping their losses, reducing their losses slightly more or less constant. It's an important thing to pay attention to when you're in machine learning lands is who your algorithm swaps in and swaps out. Let's talk about that for a minute. Let's talk about capturing the gains from ML. We have a lot of years of history understanding how to satisfy regulatory requirements and manage business risk with traditional underwriting. There's lots of advantages to traditional underwriting, and our experience is one of them. In this new world of ML-based underwriting, we have to solve those same problems. We have to give the regulators what they need to achieve their mission, which I think we all agree is an important mission. We have to be able to run our own businesses. So machine learning modelers have to know how their models work, and their managers have to know how their models are going to work. And those things, we have to figure out how to do that in machine learning land. Generally, if you look at the press that's written about machine learning, or you listen to discussions, what you hear is people talking about algorithms. So either I use toolkit X, or hey, I just use an XGBoost algorithm. You hear people talking about math because people think math is the hardest part of the problem. And it is hard. But it's not the only part of the problem. And in fact, in our experience, it's not the hardest part of the problem. The hardest part of the problem is actually doing the operational work and regulatory work of getting the model into production. The model mathematics, although hard, and don't get me wrong, it's a source of skill, there are really great tools out there that can help you build better models. Obviously, SAS is an amazing toolkit and has been for, I think, 40 plus years. And we have a toolkit environment. There's a company called Data Robot that has a really nice environment to do automatic model selection. There's a lot of things that can help you with the model build. But what you got to think about most is, okay, let's assume I can build a beautiful model. How do I actually get it into production so it works? And the key underlying point here is that explainability is everything. Machine learning models, I mentioned earlier, have one weakness, which is this: they're spiky. They have steep gradients. A better known weakness of machine learning models is that, in general, they're black boxes. You don't know why the model gave its answer. You simply know that it gave its answer. And this obviously doesn't work for any number of reasons. First of all, you end up in the press getting sued. But you also end up in front of your regulators because you haven't been able to answer either fair lending or FCRA. You don't know why the model approved Douglas. You don't know if maybe if it was because of my gender. You can't do good reporting on your model because all you have is the input and the output. And you don't know, which means you're not meeting model risk management guidelines, And you actually don't know if your model's healthy or not because you just know input and output. You don't know why. You have to actually be able to crack open the black box in order to do that. Now, to crack open the black box is to do this stuff called explainability. And explainability turns a black box model into a white box model. And explainability is really, really hard. There are people who will argue that explainability is solved. And it's solved because, look, there are tools that come out of the box that will help you explain a result. And that's true, but as I'll go into the next several slides, most of those tools have very significant weaknesses that aren't as well advertised. In fact, most of the work of explainability lies under the surface, much like an iceberg. And much like an iceberg, if you get this wrong, you could poke a relatively small hole in your underwriting, which could lead to a relatively large problem. Much like the actual hole in the Titanic was quite small. It was about the size of a tablecloth. But that story ends badly. So what I like to do is spend a few minutes talking about explainable machine learning, and I want to make sure we go into it with the goal that we are able to have a toolkit that tells our modelers, our business owners, and our regulators exactly what our model is doing, and that meets certain characteristics for the quality of an explanation that we should use as an evaluative criteria for that explainability toolkit. So let's go through some examples. Hopefully these are at least readable on your screen, and if not, I do apologize. One of the most common ways to explain models is to do what's called tree walking. And tree walking is essentially you start at the top and you go down until you get to an answer, and you count what you did. So in this case, this particular model says that risk is a function of the logical and of bankruptcy and inquiry. And logical and means you have to have both. So that says you have to have both bankruptcy and inquiry, times 40. And we add the times 40 to make the tree branch a little bit better. So look on the left-hand side of the tree. The tree starts at bankruptcy. That's called the root node. And then you have arrows going left and right. The arrow going to the left is labeled N. What that means is that bankruptcy was equal to no. And you get down that branch and you get to inquiry. And inquiry could be yes or no. So there's Y or N branches. But in either case, it's 0 because you need both bankruptcy and inquiry. So let's go to the top. And you get bankruptcy going right. This time you go to Y, to inquiry. And now inquiry is there again, because inquiry turns out to be important on both sides of the tree. It doesn't always work that way, but it does here. And you can have either no or yes. And if bankruptcy is yes and inquiry is no, you have a 0. But if bankruptcy is yes and inquiry is yes, you have a 40. Okay, what's the most important signal here? There are a bunch of different ways of computing this, but the simplest way is to do what's called counting splits, which is to go through each variable and simply count the number of times it appears as a decision criteria. In this case, bankruptcy appears once, inquiry appears twice, so inquiry is twice as important as bankruptcy, which if you look below, you'll see that bankruptcy is shown as a value of 10, and inquiry is shown as a value of 20. Sweet. I can go back to my regulators and explain that my model thinks inquiry is twice as good as bankruptcy. Sweet. Except, what if I just change the structure of the tree, and I put inquiry up top? I've still got no and yes, so inquiry no going to bankruptcy, Bankruptcy, no and yes, both 0. Inquiry yes goes to bankruptcy because now bankruptcy is the secondary factor, and bankruptcy yes equals 40. So now in this tree, there's 2 bankruptcies and 1 inquiry, so bankruptcy is twice as important as inquiry. It's the same model. It yields the same output. How is it the case that I can ask the question twice in slightly different ways and get a different answer? Now imagine you're the chief risk officer, and you are signing off that you believe you're giving correct adverse action reasons. And I tell you, well, actually, it depends on the way you ask the question as to which adverse action reason you're going to get. How do you want to ask the question? My sense is you're not going to feel good about that afternoon. So tree walking methods are easy, they're compelling, but they're inconsistent. And that's probably not going to meet the regulatory burden that we have. Another thing that people will sometimes answer is, that's okay, I'll do what's called a proxy model. I'll add a linear model in front of my machine learning model. So here's an example of that. So on the left-hand side of this chart is a 3-layer neural network. That's just a super simple neural network. On the right-hand side is the formula for a logistic regression. If you look at the right-hand side, you see that you have a B0, which is a constant, plus B1x1, which is a coefficient, and then some signal called x1, plus B2x2, which is a coefficient, plus some signal times x2, and then you can have some number of those. Logistic regressions can handle sort of 15 to 30 coefficients. And to explain a logistic regression is trivial. You just read off the coefficients. Like, if I have a really big B2, okay, B2, that means x2 is really important, and like you can just read them off. It's really simple. And so the notion is, I'll build a model on a, say, neural network, and I'll learn the powerful model that way, and then I'll stick all those signals in the logistic regression, and I'll run the logistic regression and use the LR as explainability. And so that's what those arrows show. This arrow shows that there's B1x1 is coming from one of the input layers, and B2x2 is coming from a hidden layer, which is a green. And the green dots are some complicated high-order relationship between all 4 of the input layers, and often from other green layers as well. Perfect. So, I know that X2 is a powerful signal because it came out of this neural network. This is awesome. I can write a great logistic regression. And, in many cases you can, right? Logistic regression can mimic, many of the powerful machine learning techniques. You give up some power, and exactly how much power you give up is actually a subject of academic debate at the moment. But you give up some. And you can explain it because you can read off the B2X2. Awesome. This is got to be the winning answer, except A, you have given up some power from the machine learning model. But equally importantly, you actually didn't get as much explainability as you think because X2 is some complicated function of other signals. So I can tell you, hey, borrower Douglas, the value for X2 is the most important reason that I denied you. But for me then to say X2 is some complicated interaction of DTI and number of dollars outstanding and rent, if this sort of complicated conjoint signal, which I don't understand, so you can't actually explain, using this model, why those signals exist. You're stuck in a situation where you have neither the raw power of the machine learning model, nor do you actually have the explainability of the logistic regression. So this is a little bit kind of the worst of both worlds. Okay? So at this point, people will start saying, oh, no, it's okay. I can tweak my neural network. I can force it to have no higher order interactions. I can make it all monotonic. Those are all things you can do, and they do address the problem. But if you take a Formula One engine and you stick it in a Ford Tempo, you do not have a Formula One car. At some point, the question is, why bother? Just solve the problem. There is a provably correct solution to explain all machine learning algorithms. The answer, try all possible answers. So if you have a 10 signal model, you compute your answer with all 10, then you compute it with 9 without the first one, make the first one missing, so I've got 9. Then I bring the first one back and make the second one missing, and I bring that back and make the third one missing, and then I do 1 and 2 together, or 1 and 3 together. It's called a power set decomposition. It's just really, really hard. So if you have a 100-signal model, which is not terribly complicated, and you do this brute force solution, you will have to compute the model about 10 to the 150th times. And for those of you playing the home game, there are about 10 to the 80th atoms in the universe. So 10 to the 150th is a very, very big number. So although it's provably correct, it's largely infeasible. So this is a summary slide. I don't know why I included a summary slide. It makes me feel like all consultancy. Like maybe I'm going to issue you all bills or something. But hopefully what the summary slide says is roughly what I said. But what's cool is that the future looks better than this. The future looks like either what are called local interpretable models, and the most famous one of these is called LIME. Local interpretable models ignore the global problem of understanding the model and try to understand a very specific piece of it. Like, say, for example, in the case of a credit application, they try to understand the explanation of that one particular application to provide adverse action. They don't care about what kind of model you have. They're super stable. They're hard, but they're much easier than brute force. The issue with local interpretable models is they don't do outliers very well. So a LIME explanation of our gender model is going to puke in some creative way on Mr. Dylan Postal. So there's a lot of promise here, a lot of academic research going on in here. This is clearly part of the future score. There's another set of models, which are how we do it, that are basically we call optimized relative search. You're doing an optimal search across a relative space. It's pretty awesome. They're stable. They're really fast. The problem is the public implementations of these mathematics don't include all model types. So you don't get the benefit of being model agnostic. You have to know about the model you're in. So, obviously room to grow there. But either one of these two gives you stable answers, and you trade off some various features for it, but you get the entry criterion of stability. But other than mathematical interest, there's actually a reason why one cares about explainability. And that is that you are attesting, if you're a credit risk officer, or promising your bosses, if you are a modeler or a internal risk management person, that these models are complete and correct. And you need to understand, for adverse action, but also for a variety of other reasons, exactly what are the features that drive your model. So this is an output of an optimized relative search for a client. You see that these factors are all pretty small, but this is the exact order in which they fall, and you know that no matter how I ask this question, I can tell you that for this applicant, these are the things that matter. You also need it for fair lending analysis. So let's tell a quick story here. Generally speaking, there's this common argument right now in the press going on of whether machine learning models are biased or not. Stop the press. The answer is in. The answer is yes. Machine learning models are biased for a variety of reasons, some of which are structural in nature, like we tend to have biased training sets, some of which are diversity in nature, which we tend to not have very diverse teams, but some of which are mathematical reasons. It just turns out that the reason that ML is powerful is they find subtle, non-intuitive relationships between variables. Tragically, sometimes those subtle and non-intuitive relationships are things we don't actually want in the data set. So look at these two charts. This is from an indirect auto lender. One of the factors in their model today is mileage. As the mileage of a car goes up, the risk goes up. And it's a reasonably big effect. Changing this risk index from 0.15 to 0.13. It's a pretty big relative effect. It kind of makes sense, right? Yeah. Higher mileage cars, more likely for something to go wrong. Yeah, okay, fine. You go to your compliance folks, and the compliance folks are like, yeah, fine, you can use that signal, no problem. They have also the data that shows that actually there's a little teeny effect of whether you live in state 47 or not. Now, it's teeny. It's a little small effect, from 0.138 to 135, 134. It's just not that interesting a variable, and it undoubtedly would not make a traditional model. But when you start allowing yourself to have more data, this slides in because it has a factor. So the answer is if you are in state 47, you are a slightly lower risk than if you are anywhere else in the country. Again, you go to compliance folks say, cool, I don't care. You know, the United States good. Way above redlining, no problem. So I've got two factors, both of which seem separately good. And together, it turns out that they proxy to African American. So these two variables together yield a disastrous fair lending problem, and obviously a clear moral problem as well. So you have to then ask yourself, what do you do? Like, first of all, to find this out, you have to explain your entire model. You have to know what all the interactions in your model are. Right? I just talked about how that's hard. Once you find it, you have to be able to make the argument of, okay, is this finding a business requirement? Is it legitimate? Is it not legitimate? If not, what do I do? Which ought to require you to try a bunch of stuff. Take it out of the model, put it back in the model, trim it, like all kinds of experiments. But all those experiments require you to re-explain the data, so explainability has to become part of the workflow. And the interaction between the modeler herself and whoever represents compliance inside and or the regulator all has to be much tighter. So we have to share a language and a set of tools for having this conversation. That language and that set of tools is well understood in today's world. It's called the Model Risk Management Document. And in fact, there's long-standing OCC guidance of exactly what needs to be in an MRM document. As part of implementing a machine learning model, you have to find the rules, follow the rules. You know, and you should do that in a way, in my opinion, modeling should do that in a way which makes risk and compliance more effective, not less effective. I think it is a non-starter for someone to come in and say, okay, we're going to transform our entire modeling environment, and by the way, all of you risk control guys and all of you reporting folks, I'm not going to do anything to help you. That just feels wrong to me. So that's an important implementation barrier, but it all builds on this notion to be able to have explainability and explainability reporting part of the workflow process. And while we're talking about implementation, let's do a quick shout out to my technology friends. I think a lot of times you hear machine learning and machine learning implementations, and what you hear is, oh, I need a whole bunch of new hardware. I need a whole new operating set that operating system supported. I need a bunch of tools supported that I don't have. And I got to completely redo my loan management system, and I got to pull the guts out of the origination system that nobody's worked on in 20 years. I have to do all that stuff, and oh no, it's going to take me 2 years to do that, and it cost me $50 million, and I'm doing all this. Why? Why don't I just make more loans than the current loans? It is important for people who are selling machine learning tools and for folks who are trying to implement machine learning tools to find surgical ways to upgrade only the bits that need to be upgraded. And there's a lot of different tricks to doing that. You can alias a different score, or you can use a workflow engine. There's lots of ways to do that. But I think it's really important for all folks who are selling machine learning software to think through, how do I make this as simple as possible to implement? And the big barrier, and the biggest bugaboo, and the highest check, I think, is usually, hey, all the data has to be present and perfect in production. And so before I can do one thing in ML, I have to do all the stuff. I have to build a data lake, or as I like to think about, the data wide Sargasso Sea. And that's hard. And it also turns out to not be necessarily true. You don't necessarily have to have all data. You don't necessarily have to have perfect data. You can just use the stuff you've already got and probably use it more effectively. So I think it's important to maybe disentangle the need for all the data from the benefits of getting some of the data used more effectively. Recall that 2/3 of the lift on that one client was from data they already had lying around. And they would have gotten most of that lift without adding a single new feed. There is a reason to add new data. There is a reason to add additional credit bureau data, but it's not necessarily a blocking factor. Another thing I want to make sure everyone is focused on is we have to carefully monitor machine learning models. I talked earlier about how they have really steep gradients. They're really spiky. Weird things can happen with slight changes in inputs. And if you don't actually carefully monitor your inputs and your outputs, you won't notice that. You have to monitor system health, because These may not be pieces of infrastructure that technology folks are used to monitoring. So, and it's actually pretty hard to identify in real time population drift. Those are actually pretty hard mathematical problems, but they're problems that are really important. The beauty of traditional underwriting is that it is pretty straightforward. You get it, you get the right answer, you get a consistent answer, it learns pretty quickly, and they execute pretty quickly. Those are all great features. The downside is you're giving up a bunch of mathematical power, which you could turn to increasing approval rates and reducing losses. There's a bunch of things that have to happen in order for you to be able to do that. And hopefully chatting through it a little bit today has been helpful for that. Thank you very much for listening. And with that, Mike, we'll toss it out to you for questions.
Excellent. Thank you, Douglas. Really fascinating. And I can see that we've got a lot of folks that think the same thing. There's lots of questions coming into the queue here. So I think we should just jump right into it. We've got about 15 minutes to handle some questions. And everybody in the audience, if you've got something on your mind, now is definitely the time to get it into the queue. But let's kick things off with this question. The credit markets listed are mostly consumer loans. Is there a use for machine learning in non-consumer markets?
Oh, sure. Yeah, and I'm sorry if I was unclear about that. I usually talk about consumer loans because it's just more convenient. But yeah, we have clients that have done business-to-business stuff, have done like weird stuff like factoring. Ultimately, you have a little bit the same problem, which is current lending works pretty well as long as you're willing to put the muscle power into it. And so you end up with a whole bunch of, either you end up with very, very simple models and a lot of hope, or you end up with more complicated models and a lot of people going out and reading, 401ks and reading private corporation documents, and maybe not doing the best use of including data on the principles in the model. So yes, actually the problems in our experience, the problems look pretty similar. You can use different techniques, but you still get some benefit out of it in terms of like asset valuation, things like that, but the techniques look different.
Interesting. Thank you. All right, let's see. Next question here. How do you monitor model performance against training data, and what do you look for as warning signs?
So let's go through a quick promotion process, and then answer the question. I'm going to answer the question kind of a long way around, so hopefully whoever asked it can bear with me for a second. As part of deciding to launch a new model, you're supposed to compare business results. And business results in this case require you to look across the deciles, look at approval rate, and model different approval rates, and there's a bunch of different sort of things you have to do. But by doing that, you lay out how you think the model should exceed or should beat the previous model's performance. And who knows, maybe it comes up short in some segments as well. I'm hard to say. What you're going to do then is monitor, first of all, the output performance on a delayed basis, right? So you're going to monitor on a delayed basis, does this model get the approval rates and the failure rates, the default rates that I expected from my model approval process, right? So, but that, of course, is out of band because defaults take a while. So then you're going to narrow in a little bit, and you're going to look at the distribution of inputs from across your training segments and distribution of outputs. And you're going to monitor in real time those distributions across all your signals. And now it's a little bit mathematically tricky to do this, but conceptually you're just going to count to make sure that no one has 0 bankruptcies in your training set. So if you end up with a large number of people who have 0 bankruptcies in your production set, something broke, right? Or in your training set, your score went between 3 and 7 always. And if you start spitting out a bunch of 10s in production, something broke. So how to do that is actually a little bit hard, but that's the 3 things you're going to do. You're going to have a delayed metric which captures actual defaults. You're going to have 2 real-time metrics, one of which is the expectation I have of signal distribution, of inputs distribution, and the expectation I have of output distribution.
Great. Thank you. Okay, here. Thank you, everyone in the audience. Lots of great questions here. Okay, how do you monitor your models, and what do you look for, and at what thresholds do you use before deciding something needs to be done? And what do you do to correct it, that is, retrain with new data?
Okay, so I sort of answered the first half of the question in the previous question. Exactly the thresholds you said, I think, is a function of your risk appetite and kind of the distribution of different signals. That's a hard question to answer in the abstract. What do you do? I think the first thing, what our models do is they just throw a flag and they ask some human to help them. Machines are really great at lots of things. They're really bad at understanding the causes of statistical anomalies. So, but that's, of course, although that's true, that's not the question I suspect the person is really asking. You have three options you can do. You can stop lending when you see a problem, like turn the model off. You can revert the model to its previous version, either a previous version of machine learning or the logistic regression model. But generally speaking, what you're really, assuming you're not in some weird fall off a cliff scenario, you're probably going to retrain the model. And the goal is to have that retraining process. Our clients retrain usually about every 3 to 6 months anyway. So the goal actually is that you just don't have that much time to accumulate scary data before you're going to retrain anyway. So sort of, retrain is the moderate-sized weapon to use against population drift. Complete kind of, remodeling is a slightly larger effort, but also hopefully doable.
Excellent. Thank you. All right, here, let's look. Next question. Here we go. Is there anything proprietary about the machine learning consumer lending models that are being employed, or is it just a function of data sources, time, and money?
That's a really good question. I think in general, the machine learning being done today includes some data preparation, it includes some modeling, and it should include some explanation. There's process stuff which is proprietary in the explanation space, but hopefully the math is not. So, for example, we fund Carnegie Mellon to work on Lyme publicly. They report everything they do in journals, and we don't use Lyme. So my hope would be actually that people are really focused heavily on the public use of mathematics. In the modeling itself, the math is all just math, right? Mathematicians and computer scientists making a living around the world coming up with new math. That's just math. So there's nothing really proprietary there. You might end up with process stuff or optimizations that are proprietary. But, anyone who comes in and says, hey, we have proprietary math for you, you should probably roll your eyes because that doesn't make any sense. But what does end up mattering is time, which may or may not mean money. Understanding of the process of giving credit, of monitoring credit, of kind of doing the art that we do, I think is the biggest difference between players. But ultimately, math's just math. I can give you a copy of Peter Norvig's textbook, and you can, do everything you need to do. One of my new lawyers is busily reading her way through the textbook and asking questions, and pretty soon she'll be able to do perfectly good models. That's great.
Excellent. All right, here we go. Next question. All right, good. Is there hype around data sources? For example, is social media data predictive? Is there one specific traditional underwriting variable that machine learning has shown not to be as predictive as believed?
So I think different domains of credit and different geographies have had different kinds of data that mattered a lot. Part of that's because of data availability, and probably part of it is underpinning differences in society. I am not a sociologist. I am not competent to opine on the differences in underpinning societies. I think when you look at the positive side of the ledger, the biggest variable that we all have in our traditional credit models is debt to income, D to I, and D to I should show up at the top of every machine learning model because it's usefully descriptive. What I think might be in current models that maybe wouldn't make a good machine learning model are more the point-in-time summarizations of credit bureau data. where you actually have trade line data underneath it, and you can use more complicated path diagrams. We're going to pay attention to what behavior changes over time. So I think to the extent that those are hard to incorporate in a traditional logistic regression or CART, but they're more straightforward to incorporate into a machine learning model. So I think probably that's the biggest data difference. There is certainly hype around data sources, and I think part of what a good long-term machine learning plan would include is rigorous and principled testing of different data sources over time to discover those that are most useful or those that have the most usefulness divided by cost ratio. I mean, like, those are the things I think are really important to pay attention to over time.
Great. Thank you, Douglas. And okay, good. Let's tackle this question. What kind of data should lenders look to when using machine learning? How do you determine when it makes sense to use alternative data?
Well, so a little bit. I think I just answered that. There are mathematical ways to rigorously test the value of data sources, and it is not the case that all data sources have unique values. Some don't. Some data sources are agglomerations of other data sources. It's also the case that value can be found from kind of dirty, relatively esoteric data. And keep in mind that a huge amount of the lift for early models in machine learning comes from data you've already got lying around. So don't necessarily start from the, oh, hey, how does alternative data fit into this question, but rather start with, hey, what do I have lying on the floor already that I could just reuse?
Gotcha. Okay, good. All right, we are getting close to the top of the hour here, but I think we've got time to squeeze another question or two. Here, let's take this one. For model risk purposes, what would you include in a model document, and what would you leave out as proprietary?
So model risk management documents usually developed by the modeling team in the organization itself, so I'm not sure why you leave anything out. I mean, so I'm not sure I understand that question. If there's a follow-up to that and we can fit it in, that's great. I mean, if the question is specifically about what Zest does, I mean, we follow the guidance. So I'm not sure I understand that question. So if there's a follow-up to that question, send it on in. But you can try something else for now.
Okay, very good. Let me take a look through here. What else are we taking a look at? Okay, very good. Here we go. Do you think loan portfolios created through machine learning will fare similar, better, or worse than traditionally underwritten ones in the next economic downturn?
So anyone who tells you that they predicted 2008 is a liar. Anyone who tells you that they know why 2008 happened is either a true visionary or a liar. In general, it doesn't look like loans that were underwritten with traditional underwriting did worse than loans that were 100% judgmentally done in the last downturn. The difference between judgmental underwriting and logistic regression is far greater than the difference between logistic regression and machine learning. So if you believe in that logistic regression will perform acceptably in the next downturn, the odds are good that ML will perform acceptably. Will it be worse, better, or the same? Hard to say, but it's unlikely. There's no reason to believe it would be worse. It's not instantly obvious. There's a lot of reason to believe it would be better, except that if you're doing good model monitoring, you might notice more quickly that something is going awry because you have a little more data to play with. And by noticing more quickly that something is going awry, you might be able to do something more quickly. So maybe you could argue that ML would be better in that case, but that's entirely speculation.
Gotcha. All right, good. Thank you, Douglas. And I think that really brings us right about to the top of the hour. So we always love to bring these programs in close to schedule as possible, respecting everyone's busy days. But this has been a really great, the whole program has been excellent, but this has been a really active Q&A session, which is always a really nice indication that what we're talking about here is resonating with the audience. So thank you, Douglas, for being here. Thanks for a great hour of presentation discussion, and thank you, everyone in the audience, for participating so enthusiastically, actually. It's really, really nice to see. And please keep an eye out. We'll be sending you a follow-up email in the next day or two that's going to have a link to the recording of this event, so you can listen to that in the future, and encourage you to do that at your leisure. And with that, I'll wrap it up. Wish everyone a wonderful rest of the day, and I hope you will join us again here very soon. Thanks so much.